By following the proof of Nash's theorem through Sperner's lemma and Brauer's fixed-point theorem, we can derive an algorithm that computes epsilon Nash equilibria. However, the running time guarantees for this algorithm are exponential in the number of pure strategies of the game, and that's rather poor. The obvious question is, can we do better? Is there maybe an efficient algorithm for computing an epsilon Nash equilibrium? Nobody knows the answer to this question. However, there is some evidence that computing an epsilon Nash equilibrium may in fact be a computationally hard problem. So we maybe should not expect that an efficient algorithm exists. Certainly, if such an efficient algorithm would be found, this would be a stunning surprise and one of the biggest discoveries in the foundations of computer science. You may know that if a computational problem is NP-hard or NP-complete, this is taken as a strong indication that the problem is difficult and, based on our current understanding, the existence of an efficient algorithm is very unlikely. The problem of computing an epsilon Nash equilibrium is not NP-hard, but it is difficult in a similar sense. The problem is PPAD complete. To explain what this means, I have to explain what the complexity class PPAD is. To do this, I will start by telling you about the prototypical PPAD complete problem, which is known as end of the line. The definition of this problem, end of the line, is as follows. The input consists of a directed graph in which every vertex has in degree and out degree at most 1. And also part of the input is a specific vertex or node V. And this particular condition on the in degree and out degree of the nodes means that the graph only consists of isolated nodes, simple paths, or simple cycles. So this could be an example of such a graph. We could have a path, we could have another path, we could have isolated nodes, and we could have a simple cycle. But this is the only thing that can exist. So there can be no branching, for example, because that would require a node that has at least 2 outgoing edges. And this is not allowed. Okay, so the output that you should produce is the following. If this node V has the same in degree as it has an out degree, so either it has in degree 0 and out degree 0, so it's an isolated node, or it has in degree 1 and out degree 1, so it's like in the middle of a path or cycle, in that case you don't have to do anything, so you just output V itself. So this is not an interesting case, it's part of the definition for technical reasons. The interesting case is when V has an in degree and an out degree that are not equal. So for example, V has out degree 1 but in degree 0. In that case, we have to output another node, so not V, but some other node, that also has an in degree and out degree that are not equal. And this node has to exist. Consider this example. If we just started V and follow this path, the path has to end somewhere, and that would be a valid answer to this problem. But it's not the only answer in this example. Any other start or end point of a simple path would be a perfectly fine answer as well. So here we have this other path of length 1, and both the start and end point of that path would be possible outputs as well. Now, as I stated this problem, it's actually not a particularly interesting problem, because what is an easy algorithm to solve this? Well, just go through every node of the graph, check if the in degree is equal to the out degree, and if they're not equal, you can output that node. And how much time does this take? Well, you just need to check each node once, and you can make each check, say in constant time. So this will just require linear time in the size of the graph. So that's very fast. So to make this problem interesting, we have to encode the input in a different way. And this input representation that I assumed here was that the graph is somewhat given in explicit form. But what if we encode the graph in an implicit way? Now, this will look a bit strange at first, but just stay with me for a minute. Here's a new problem. The input consists of two logic circuits. Let's call them P and S. And each of these circuits has k input bits and k output bits. I also require that the size of these circuits, so the number of logic gates in each circuit, should be polynomial in this number k, in the number of input and output bits. Now, we can interpret these circuits as encoding a graph that we've seen on the left-hand side. So here's the interpretation. We assume the graph has 2 to the k nodes. That means an exponential number of nodes. And each node corresponds to a bit string. So we have an identifier for each node, and that's just a bit string of length k. Now, what do these two circuits do? The way to think about these circuits is as follows. The circuit P computes potential predecessors of nodes. So you put in the identifier of a node, and you get out an identifier of a potentially different node that is a potential predecessor of the node you put as an input. And the circuit S computes potential successors of a node. So P computes potential predecessors, and S computes potential successors of a node. And now the edges of the graph are defined as follows. An edge in the graph exists if the circuits P and S agree that this edge should exist. If they disagree, the edge does not exist. So what does this mean? Well, we have an edge from A to B if and only if S of A equals B, so the successor of A is B, and P of B is A, so the predecessor of B is A. So the two circuits agree that this edge should exist. And this might seem super artificial, but the purpose of having these two circuits encoding the graph in this way is that this automatically guarantees that the graph has the properties that we wrote down on the left side. So if we encode the graph in this way, it guarantees that the in degree and out degree of each node is at most 1. Okay, so this is our input now. Instead of having the graph in explicit form, we just get these two circuits. And the output is just as before. So we're looking for a node that has in degree that is not equal to the out degree. And this node V, say, is just the node that is encoded by this bit string 0000. Because now the graph has exponential size in the size of the input, this is no longer a trivial problem. Because now if we would search every node of the graph, we could still do that, but it would take exponential time, so it would not be fast anymore. We could, of course, also just follow the path that starts at V to find the endpoint of that particular path, but that path could also have exponential length, so that could also take a long time. And what else could we do? I mean, I suppose the only other possibility would be to somehow analyze these circuits in some clever way to find out where endpoints of paths are, without actually looking at all the nodes or following an exponentially long path step by step. But nobody knows how to do this. Now, an important note here is that this is a bit different than maybe if you've heard in complexity theory about decision problems before, where you get some input and you're supposed to say yes or no. For example, you get a graph as an input and you're supposed to say whether the graph is a Hamiltonian cycle or not. And this is a bit different because we know that this point we are looking for always exists. There's no question about it. If the node V has an in degree that is not equal to the out degree, then there must be another vertex that has the same property, simply based on a parity argument. So it's not a decision problem. It's not a question of does this node exist. We know it does. The question is to find it. So it's a search problem. So let me formally define what a search problem really is. We call a problem, a computational problem, a search problem if each instance x has a search space Sx associated with it. And the search space is just a set of bit strings that have polynomial length in the size of the input. And valid solutions are given by some non-empty subset of this set Sx, and we call this set, say, Qx. So those are the valid solutions. And there's an additional technical requirement here, which just says that it should be possible to efficiently check whether a given bit string is in this subset Qx or not. And in the case of other complexity classes like NP and so on, we heavily use reductions to make arguments about the relationship between problems. And also for search problems, we have such a concept of a reduction. And a reduction from a search problem P1 to a different search problem P2 consists of a pair of polynomial time computable functions, say f and g, where for every x in P1, so we have some instance of the first problem, we have f of x is in P2, so we can transform, using this function f, an instance of the first problem into an instance of the second problem. Okay? And then we use the other function to translate solutions back from problem 2 to problem 1. So for every valid solution, y of this second problem, P2, for input f of x, we must have that g of x and y is a valid solution of the first problem, P1, for input x. Right? So we can transform instances of the first problem into instances of the second problem, and then we could solve the second problem, and then we could translate the solution back into a valid solution for the first problem. So this is these jobs of these two functions f and g. F goes from the first problem to the second problem, and then g goes from solutions of the second problem to solutions of the first problem. And if such a reduction, a polynomial time reduction exists, then we write that P1 reduces to P2 in polynomial time. And with this, I can finally define this complexity class PPAD, which I mentioned before. And PPAD stands for polynomial parity arguments on directed graphs. And you might be able to guess where this name comes from. And the complexity class PPAD consists of all search problems that reduce to this problem end of the line that I told you about. Right? So everything that reduces to this problem end of the line is in this class PPAD. And furthermore, the class PPAD complete which will be the class of sort of the most difficult problems in this class PPAD. So these PPAD complete problems consist of all the search problems in PPAD to which end of the line reduces. So these are problems which are essentially equivalent to this end of the line problem. They have the same features, the same difficulties as end of the line. And here comes the big result now. And I'm not going to fully prove this, I'm just going to state it and give you some vague intuitions about parts of these arguments, but not all of them. So the big realization here is that this problem Nash, the problem of finding an epsilon Nash equilibrium, is a search problem, because we know these epsilon Nash equilibria exist, it's just a question of finding them. And we had this other problem, Brouwer, which was finding an alpha approximate fixed point of a function. And again, we know these fixed point exists for continuous functions that map from a convex compact set onto itself. So it's a search problem again. So this problem Nash reduces to the problem Brouwer. And when I say this, I should be slightly more precise, I suppose, on what this problem Brouwer really means, because how do you even encode an arbitrary continuous function as an input to a computer? Well, you can't. So what you need to do is you need to discretize the domain of the function. And then, for example, you can give the computer an encoding of this function in form of a logic circuit. And for each discrete point, the computer could plug in the values into the circuit and see what comes out. And that would be the value of that function at that point. And to make this a continuous function, we just assume that the function value at points that we didn't discretize, so in between, we just interpolate linearly the function value, for example. Okay, so these are some technical details about input encodings. So essentially, we can kind of picture it like this. We have this x-axis here, and we take a few discrete points and the function values at those points, and then we can evaluate the function at those points, and in between, we just assume that the function is linearly interpolated. Okay, so now you might be able to guess where this is going. So we take Brouwer, and in fact, we realize that Brouwer reduces to the problem Sperner. Okay, so what is the problem Sperner? The input to this problem is a circuit, and the circuit simply translates identifiers of vertices of this subdivided simplex into a color. So you put in the identifier of a vertex and you get out the color of that vertex. And then your task is, of course, to just find a fully colored subsimplex. So that's the problem Sperner. And not surprisingly, Brouwer reduces to Sperner. And then the least surprising part of all of this is that this problem Sperner reduces to the problem end of the line. And the reason for this is quite simple. We've seen this in the second proof of Sperner's lemma in the video where I showed you how Sperner's lemma is proven. And what we saw there was actually this graph that consisted of isolated nodes and simple paths and simple circuits, and the fully colored simplices were exactly the endpoints of these paths. So it's not surprising that there's a deep connection between Sperner's lemma and end of the line. Now, the big result, the really big result, and relatively recent result, is that all of this also goes in the other direction, right? And so this problem end of the line, in fact, reduces to Nash. And this is a complicated proof, but it was really a breakthrough result. And what it shows is that all of these problems, finding an epsilon Nash equilibrium, finding alpha approximate fixed points, finding fully colored subsimplices, and finding the endpoints of lines of an implicitly given graph, all of these problems are in fact computationally equivalent. They are all PPAD complete. And so an algorithm for any of those problems would lead an algorithm with a similar performance for all the other problems. And just as when we show that something is NP-complete, we take this as an indication about the computational hardness of the problem, you should think of this as saying something about the computational hardness of this problem of finding epsilon Nash equilibria. And in particular, it means that currently it seems completely out of reach to find efficient algorithms for this problem. And it might very well be that there are no such algorithms. Having said that, PPAD completeness is not quite as strong a statement as NP completeness, so who knows?